Great. Oh, I feel so special. All right. So yeah. So first, I really want to thank the organizers for this series of meetings. I think this has been incredibly beneficial to the field, and I'm really pleased to be able to participate in it. So what I want to tell you about today is some work that's very much along the lines of what we've been hearing the last couple talks, though made a little bit more concrete. So the goal of this theme of work in my group is really to construct models that have sufficient detail that one can ask specific design questions concerning the interplay of computation, energy consumption, and speed in models that are actually reflective of the sorts of circuits that we use to do computations, like on the computers that I'm running this talk off of. So some of this work is published last year and led by my former student, Chloe Gao, in this PRR, and about half of it is unpublished work that I'll talk about. Okay, so for me, this is really motivated by the observation that we as a civilization use an incredible amount of our energy budget on computation, and this is growing. There are estimates that the majority of our energy consumption will go into computation in the next 20 years. And so one would like to create devices that increase the efficiency by which we do those calculations. And indeed, there's been a tremendous amount of progress in that direction since computers were first invented. This is something I learned when I started thinking about this problem. This has been formalized, this increase in efficiency energetically has been formalized in a relationship known as Kumi's law. This is the increase of the efficiency per bit operation in terms of the energetic cost, and it grows exponentially, starting with the old vacuum tube computers and increasing all the way to the iPhones that maybe some of you are streaming this talk off of. So if we want to keep going further, we're going to eventually start running into fundamental laws, and we've heard one of the most famous ones, that due to Landauer, which tells us that if we were doing things completely reversibly, that there's a fundamental bound on how much heat we have to dissipate per bit operation. But that's in a reversible limit, and current computing technology is nowhere near that, nor would we really want it to be, because we don't really want to do a reversible computation, because usually that would imply that it requires an infinite amount of time to do it. But we're in luck. The people in this meeting have developed theories and perspectives that tell us how to think about efficiencies and energy flows in small devices and happening at finite rates. And just to list a couple that have come up, there are thermodynamic uncertainty relationships that tells us how much energy we have to dissipate if we want something to go at a finite rate. If we want to actually do a non-equilibrium process and do it with some accuracy, there's going to be a fundamental energy consumption cost to it. And if we want to speed up some process, this is just one example of a so-called speed limit theory, or a speed limit theorem, one due to people in my group, which tells us if we want to increase the rate at which we're doing some process, we're going to need to pay a price there too. So, the entrance into this work for me was really trying to think about how we could bring these sorts of statements to bear on the physical design questions associated with current circuit technologies. And the thing you run into very quickly is that modeling a logical circuit like that that I'm running the computer off of, it's actually really hard, because those devices are small, they're working in nonlinear far from equilibrium regimes, and they're fundamentally quantum mechanical. And a lot of the simplifications that working near equilibrium provide us just aren't valid anymore. So in fact, if you go and you open up an IEEE journal article, somebody actually thinking about electrical engineering and building circuits, predominantly the assumptions that are invoked to study the noise in those operations will invoke this so-called Johnson-Nyquist relationship. That's what I show here, which is just a statement of the fluctuation dissipation theorem, that the fluctuations in some current I are determined by the temperature that the device is at and the conductivity of some channel G. But that doesn't hold if the system is driven far from equilibrium. And my group has thought a lot about those sorts of response problems. We heard Jordan talk about this a couple days ago, that when you're away from equilibrium, fluctuation dissipation relationships like this don't hold anymore. And so you can have a decoupling of the scale of fluctuations, say in a current, and the response of that current to an additional applied voltage, like the increase of a conductivity as I increase the voltage. So just knowing, say, material properties like the conductance curve isn't going to be sufficient to really tell me what the noise in those models are. Additionally, if the models are actually describing quantum mechanical degrees of freedom, similar difficulties arise in trying to write down response to understand the origins of fluctuations. And so, inferring in any kind of simple way how noise comes in and changes our understandings of speeds and energy consumptions and accuracies is going to be nuanced. We're going to have to try to build detailed models to really understand this directly. And so that's what we started to do. So to give you a quick overview of current technology, almost all chips use so-called MOSFET transistors. These are complicated metal oxide semiconductor field effect transistors. What that means is it's a 3-junction device. There's a source and a drain that drive a current through some semiconductor, and a third electrode, usually passivated by the metal oxide, that just acts to manipulate the energy of the electrons in that orange semiconducting region. So if you do a thought experiment where you imagine taking that device, which currently exists on hundreds of nanometers, say, and shrinking it down by a factor of 10, say having feature sizes of about 20 nanometers. Well, now the electrons that come out of the source and enter the drain actually do so fairly ballistically. They're, the scattering length of an electron through something like a silica transistor with typical vacancy densities is about 50 nanometers. So if the feature size is less than that, you basically have ballistic motion. If you start making pieces of semiconductors small enough, they become quantum dots. The levels become very discrete. And so to a very good approximation, when you actually are thinking about scaling down current technology to small scales, what you end up with can hybridize between a source and a drain with an energy, a self-energy of the electron in the little quantum dot that can be manipulated by an input voltage. And that if you actually solve the electrostatic problem carefully in the limit that the capacitance of the metal oxide film is high, it really is a linear function of that, that input voltage. So you could work out in a high temperature limit and in a limit that the electrodes are big. So you have a wideband limit. So the resultant rates are Markovian, that this is boiled down to a simple hopping process. So you have rates to hop on and off of the dot into the source or into the drain, and those rates obey detail balance. And as a consequence, you'll have a fluctuation theorem. And indeed, Pierre Gaspard has worked the consequences of such things out for this resonant level model long ago. If you manipulate the input voltage, you actually get a thresholding behavior like you'd hope to see in a transistor. So we could use this as a basic building block for then scaling up logical circuits. I'll note that you'll probably see in the next talk alternative perspectives of building simple models for logical circuits that are thermodynamically consistent also. These, I think due to our next speaker, take a similar, spiritually similar, though practically distinct approach where detailed balance and phenomenological current voltage relationships are invoked to get the same sorts of behaviors. Okay, so we could start coupling these transistors, models of transistors together and actually create logical operations like a simple NOT gate. You get that from coupling N and P type semiconductor together, like in the arrangement like I show here. In the resonant level model picture, those are just a couple dots with potential tunneling elements between them, hybridized with a source and a drain. And now we're going to use, in addition to an input voltage, an output capacitor that can charge and whose state we could read off. And then that will give us a means by which we can perform logical bit operations. Specifically, that capacitor can be charged with some constant capacitance. And if you measure the resultant output voltage as a function of the input voltage, it exhibits what the engineering community would call a voltage transfer curve, characteristic thresholding, where a 0 input returns a 1 output, or a 1 input returns a 0 output. That's the logical NOT operation. And if you threshold that with some small parameter alpha, you can turn that into a bit operation, mapping in the voltage in to an X and the voltage out to some Y. So then you're off and running. You can actually then start asking in a reasonable physical model of an actual circuit with thermal noise effects put in correctly, such that it obeys fluctuation theorems. You start asking about interplays between speed, dissipation, and accuracy. And just to see that something you'll anticipate, that is, as you start driving the voltage, the currents with smaller affinities, thermodynamic affinities, here, what we'll largely be focusing on is changing the drain voltage. That's going to be the energy scale, which when taken large returns something in a deterministic limit, and when taken small on the scale of thermal voltages, this VT, will give us something that corrupts accuracy, though at the cost of decreasing energy consumption. And you can kind of see the consequences here just in the voltage transfer curve, that as we start driving the system with energies approaching thermal energies, the logical operations become more smeared out. These voltage transfer curves broaden. Okay, so let's first talk about just some of the energetics of this NOT gate. So we all know how to compute heats from the typical stochastic thermodynamic definitions. In this case, one can write down all the cycles, and it takes a specifically simple form associated with just a couple currents and the associated affinities. The heat, if you are starting from a state where the capacitor is discharged and you plug it in, first has to charge that capacitor. So there's essentially reversible energy of charging that scales like the drain voltage squared. This is just what you get from the reversible work of charging a capacitor, whose ideal, so that capacitance is a constant. But in addition, because it's a 3-terminal device, there are currents that still persist even in the steady state. And as a consequence, there is heat that is dissipated. It turns out that the excess entropy production, the entropy production that occurs in the steady state, becomes exponentially suppressed as I increase the driving force. This is something that I wouldn't have expected. I kind of naively expected that if I increase this driving voltage D, that I would have correspondingly got a larger entropy production, as you might expect from the equation I've written here, that the entropy production is proportional to VD. But this comes as with an offsetting factor that as I increase that drain voltage, I actually suppress the currents that flow. This is a consequence of the overlapping Fermi functions that become out of resonance as the voltage becomes very large. And so there's an interplay, actually. There's the reversible charging behavior that scales like VD squared, and the irreversible entropy production that actually gets suppressed as I increase the driving voltage. And as a consequence, at different times, there's a non-monotonic relationship between the heat and that driving voltage. So higher bias gives us higher charging energies, but generically smaller leakage currents, smaller excess entropy productions. In addition to the energetic consequences of this model, one can talk about the dynamics. So how long does it take to charge? That's shown on the left. This is a reflection of the increasing time to charge as I increase the driving voltage is a reflection of the lowering of the current that was alluded to on the previous slide. And one can work out in this essentially a scaling relationship for the time to charge, the mean first passage time to charge as a function of that driving voltage, and it scales exponentially. We can associate time-dependent error rates if we were to make a measurement on that NOT gate at different times while it's charging. What sorts of errors would would we expect? And these get suppressed exponentially as we drive the system with larger energy scales. Okay, and just for the information theory aficionados, we've introduced a fairly arbitrary definition of errors. If you might use a much more sophisticated definition of errors, like the channel capacity for this NOT gate, basically the same trends hold too. And these sorts of things are in the initial paper. But what I want to spend the rest of my time talking about in the last 10 minutes or so is really bringing now to bear the machinery of stochastic thermodynamics on this problem. We have a model that is faithful to real device physics and whose fluctuations are thermodynamically consistent. So now we can ask, if we use notions of, say, thermodynamic uncertainty principles to ask about device efficiency, what can we learn? What sorts of guiding principles do we tease out? Specifically, can we say something concrete about the relationship between energy consumption and performance? Okay, so what we're going to look at in the first case is invoking one of Jordan and Todd Gingrich's thermodynamic uncertainty principles that associated with bounds on mean first passage times. This is the time to reliably have that logical operation, the charging of that NOT gate. And the uncertainty we're going to look at is the mean of that first passage time relative to its variance that should be bounded through an uncertainty principle by the heat that's released. And so, this system is an interacting system due to the charging energy on the capacitor, but nevertheless, the Hilbert space of the system is small. So one can do exact diagonalization calculations to propagate that whole first passage time distribution. And you see that here for increasing driving voltages from the left to the right, from the blue to the yellow. And from those distributions, you can pick off the mean and variance. And what you find is that charging is best constrained under intermediate driving forces. This is essentially a consequence of that different scaling behavior between the entropy production, the leakage current portion of the operation of the logical gate, and the just increasing reversible charging energy you find with increasing driving voltage. So these curves show in the crosses the ratio on the the crosses are the heat in units of thermal energies. The symbols are the measure of the uncertainty associated with the mean first passage time to charge. And there are fairly weak bounds. They show you that, for example, there is an inherent asymmetry in the system going from a logical operation that takes you from a 1 to a 0 or a 0 to the 1 is not the same. This has to do with the intrinsic asymmetry associated with P and N-type semiconducting channels, which is kind of interesting. And at least for the 0 to 1 transition, there is a maximum, a peak efficiency that tells you to operate your logical gate at 5 kBT in this case. Okay, what else can we do? So we have this model for one NOT gate. If you couple them together, you get a minimal model of an energy or a memory storage device. This is essentially because two NOT gates hooked together, like I show in the upper left, have the potential to settle into two symmetry related but distinct steady states. If the blue output a 1, that 1 would get turned into a 0, which would feed in a 0 back into the blue. That's one stable orbit of the coupled NOT gates. But the other parity is also stable. If the blue outputted a 0, that would get turned into the 1, which gets fed back into the blue. So these are two degenerate states, and thus, and if driven with sufficient energy, will be stable, then thus can be used to store memory. And just to show you how that works, if the driving voltages are small, essentially there's no way to store memory, but if we increase that driving voltage, you start generating a bistability. This turns out to be a pitchfork bifurcation in the dynamical systems language that emerges in this, this dynamical system. Those states become more stable as I increase the driving voltage to the point where I can actually retain memory for some amount of time. So then we can ask, well, how much time can I keep that memory pure? How long does it take before the memory gets corrupted? Is that going to be bounded by the heat that's dissipated as I drive this stationary orbit? And to do that, we have to create some more exotic numerical tools here. This interacting system Silbert space is a little too big to just study with exact diagonalization approaches. So we have been using more compact tensor ansatzes with trotterization for the application of the gates or the master equations to propagate the system.
Couple more minutes.
This is okay. What was that for?
A couple more minutes.
Okay, great. Right. So this is just a fun movie to show what those relaxational dynamics sort of look like. Again, if you work at small drive-in voltages, you don't have multiple stable states, but you do generate that bifurcation at large driving forces. So one of the first ways of assessing how efficient this memory storage device is operating would be to compare it to, say, a dissipation time uncertainty principle like that due to Velasco and Esposito. This says that the entropy produced over the course of some survival probability or some survival time should be greater than 1 in thermal units. If you plot that versus the blue curves, which are the mean first passage time to flip the bit, you find that indeed it's bounded, though not sufficient, not very closely. In fact, you get a much better estimate of the survival or the time to flip or the time to create an error just by making a very naive equilibrium like Cramer's estimate, just saying that the waiting time is given by the likelihood of seeing the rare event that takes you over the barrier in that bistable orbit. You can bound it from below with a refinement or a rate enhancement bound due to my student Ben Guzman-Speck that tells you that the rate enhancement associated with coupling to a dissipative process is just bounded from below by the excess entropy produced. And so this is a fairly tight bound, actually manifests the fact that at large driving voltages, you actually, in some sense, approach an equilibrium state because the leakage currents get so small. All right, so then just to kind of wrap up, these things can be built up modularly to look at more sophisticated logical operations, like the bit storage and erasure problems you can generate with a so-called D flip-flop circuit. We can compute errors associated with feeding in a string of bits and reading them back out, as well as the heat that's produced over the course of those operations. Because we have a microscopic model, we can ask about the mechanisms of those errors. These turn out to, in the case of memory storage and erasure, these turn out to be the spontaneous symmetry breakings in the orbits of these stable cycles that at low driving voltages are often to occur. And we can play fun games associated with how correlated those errors are as they propagate through sequential circuits, computing things like correlation lengths in the gate space associated with errors being propagated. Okay, so I'll go ahead and skip this and just end on some conclusions. So what I would like you to take away from this talk is that we have a testing grounds for thinking about interplays between energy consumption, errors, and dissipation that really is reflective of actual ways we do computations digitally. So this initial paper was published last year. We have follow-up work applying these thermodynamic uncertainty principles and speed limits in some upcoming work. So the most recent work was headed by my postdoc, Philip Helms. The initial work was done by my student, Chloe Gao. And all of this was really motivated through conversations with Gavin Crooks. He's really the person who put this problem on our radar. So I'd like to thank him too. All right, and with that, I'll be happy to take questions.